Dear students, today we discuss the relation between the atomic polarizability alpha and electric susceptibility chi e of a linear dielectric medium. Here we have the two cases, that is our linear dielectric medium is having higher density and also the linear dielectric medium having very low density. We first discuss when the density of the molecule in the linear dielectric medium is very low. When the density of the molecule in the dielectric medium is very low, which means the interaction between the molecules in such medium can be neglected. Because the molecules will be sitting far away, therefore the density will be low, therefore the interaction can be neglected. Okay, here we can write the polarization is proportional to the field E. That is, our polarization P can be written as epsilon 0 chi E and E. Here chi E is the electric susceptibility. Let me put this is equation 1. Here the polarization is due to the external electric field. Okay. If the dielectric medium consists of atoms or nonpolar molecules, then the molecular dipoles are formed. The induced dipole moment of each such dipole, that can be written as small p, that is equal to alpha E. Let me put this is equation number 2. As I said, our dielectric medium consists of a small number of molecules. Density is very low, and after the application of the electric field, molecular dipoles are formed, and if P is the dipole moment of one such molecule, then that dipole moment is given by this expression. Now the question is, what is the relation between this atomic polarizability alpha and electric susceptibility chi e? We have some information that P, capital P, is a dipole polarization, that is nothing but the dipole moment per unit volume. And P, this is nothing but the dipole moment per atom. And if this dielectric medium consists of n number of atoms per unit volume, that is capital N, number of atoms per unit volume. From these relations, I can write this polarization P can be written as N multiplied by P. That is, this capital P polarization is equal to N multiplied by number of atoms per unit volume into dipole moment per atom. This is put equation number 3. Now, if P is this one, I can replace this dipole moment by this expression. Therefore, our P is equal to N alpha E. Maybe this is our equation number 4. Now you can compare the equation 4 and equation 1 because both gives the polarization, total polarization P. Therefore, by comparing these two equations, you can easily write epsilon 0 chi e E, that is nothing but our equation 1, is equal to n alpha E. Here this A and E can be cancelled. The remaining term is chi E is equal to n alpha divided by epsilon 0. This is a relation connecting the atomic polarizability alpha and the electric susceptibility chi E. This expression is valid only in the case where the density of the molecule is low. Okay, actually this expression is not a general expression. That is, this expression cannot be applied in all cases. If the density of the molecules in the dielectric medium is very high, then we have to see for the another relation. That is the second case. We will derive the relation between the susceptibility chi E and atomic polarizability alpha in the case of linear dielectric medium having very high density. That is, when the density of the molecule in the dielectric medium is very high. The relation that is connecting this chi E and alpha, that is, here we will derive chi E and relation connecting chi E and alpha. From this relation, we will derive the Clausius-Mossotti equation. This equation is nothing but this equation relates the microscopic property, that is the polarizability alpha, to the macroscopic property, that is dielectric constant R. That is, the Clausius-Mossotti equation is nothing but that is the relation connecting the polarizability and dielectric constant epsilon R. This polarizability alpha is a microscopic property and the dielectric constant epsilon R is a macroscopic property. For this, consider a dielectric material having large number of molecules per unit volume, that is having higher density. Okay, fine. This is our dielectric material. This is having a large number of molecules per unit volume. The polarization in such medium can be written as P is equal to epsilon 0 chi E E. This is equation number 1. Actually, this electric field E is the macroscopic electric field. There is a resultant electric field on the dielectric medium. We assume that each molecular dipole is situated at the center of the sphere of radius r. This is our dielectric medium, and after applying the external electric field E, this dielectric medium gets polarized, and we assume that each molecular dipole is situated at the center of a sphere of radius r. Therefore, I can write a large number of dipoles are there. Density is very high, large number of dipoles are there. I consider any one of the dipole, and I believe that this dipole is situated at the center of a sphere of radius r. This is radius r. The electric field due to this single dipole E self, this is nothing but this is E self, because the electric field due to this single dipole. The electric field except this dipole can be written as E else. E else. There is an electric field other than this molecular dipole, single molecular dipole is known as E else. Therefore, the resultant electric field I can write E is equal to E self plus E else. This is the resultant electric field on the sphere, that is the electric field due to this dipole plus electric field due to the other dipoles, that is E else. Or in another way we can say that E self is the average electric field due to the polarized sphere plus E else means average field due to the polarization itself. This E else okay. Here also I would like to note on one more point. We assumed that each molecular dipole is situated at the center of a sphere of radius r. Then the molecular density can be taken as n is equal to 1 by 4 pi 3 1 by 4 pi 3 pi r cube. There is a molecular density in this dielectric material, which means one can atom can occupy the volume 4 by 3 pi r cube. Okay, and this E is the resultant electric field on such a sphere. Here we can note on that also. This E is the resultant electric field on the sphere. Okay, let me write this is equation number 2. This E self is the microscopic electric field and E else is the macroscopic electric field. Then the dipole moment of a molecular dipole, that is P is equal to induced dipole moment. This P is equal to alpha E else. The dipole moment induced here is because of this external electric field. That external electric field is E else. This is equation number 3. Okay. Actually, if there are n dipoles having the dipole moment P, then we can write if there are n dipoles each having dipole moment, then polarization P can be written as n times P. Question number 4. here I can replace this P by this expression, that is put 3 in 4. The equation 4 can be written as polarization P is equal to n times this alpha ELs. This is equation number 5. Because of the polarization, the molecular dipole produces its own electric field. That is, we are talking about the non-polar molecules. After keeping in a electric field E, dipole moments are aligned, negative, positive. Then each such dipole moment or each molecular dipole produces its own electric field, and we assumed that each such dipole is situated at the center of a sphere of radius r. Then now let us say this is a field due to a polarized sphere. That field is nothing but the E self. Okay, field due to the polarized sphere, we have already derived the expression. That expression is E self, that is equal to minus P divided by 3 epsilon 0. Okay, this is here I would like to note down those points here. That is, because of the polarization, molecular dipole produces its own field, that is given by this expression. Or this is the electric field produced because of the polarization of the molecular dipole. Let me note down here. This is equation number 6. Now, this P in this equation 6 can be replaced by this expression. Therefore, E self, put 5 in 6 minus, instead of P, n alpha ELs divided by 3 epsilon 0. Okay, let me put this is equation number 7. Now I substitute equation 7 in this equation 2. Equation 2 is E self plus E else. Instead of E self, I substitute this expression. That is, put equation 7 in equation 2. That is, equation 2 is here. Instead of I will write equation self once again. E self plus else. This is equation 2. Then if I substitute this expression here, minus n alpha E else divided by 3 epsilon 0 plus E else. Okay, I can take E else outside. E else 1 minus n alpha divided by 3 epsilon 0. Or I can write E else, that is a macroscopic field, E divided by, bring to left side, 1 minus n alpha divided by 3 epsilon 0. Okay, this is equation number 8. Okay, now if you look at the expression 5, It contains P is equal to N alpha E else. Let us substitute equation 8 in the equation 5. I can replace E else by this expression. That is, put 8 in equation 5. That is, our P is equal to N alpha is there. N alpha, instead of E else, we can use this expression 1 minus N alpha divided by 3 epsilon 0. Let me put this is equation number 9. Now let me compare equation 9 and our equation 1. Both represent the polarization of this dielectric medium. That means LHS of these equations are same. Simply I can write epsilon 0 chi E is equal to N alpha E divided by 1 minus 3 alpha by N alpha by 3 epsilon 0. Okay. It is epsilon 0 chi E is equal to N alpha E divided by 1 minus N alpha divided by 3 epsilon 0. That is, here we have compared equation 1 and 9. Now rewrite this expression. The last equation is this one. Here E and E can be cancelled. The remaining term is epsilon 0 chi E is equal to N alpha divided by, I multiply the denominator, 3 epsilon 0 minus N alpha divided by 3 epsilon 0. 3 epsilon 0 comes in the numerator. Epsilon 0 chi E is equal to 3 epsilon 0 N alpha divided by 3 epsilon 0 minus N alpha. Here this epsilon 0 and epsilon 0 get cancelled. Therefore this chi E can be written as 3 N alpha divided by 3 epsilon 0 minus N alpha. Okay. This is the relation connecting electric susceptibility chi E and atomic polarizability alpha in the case of a linear dielectric medium having higher density, very high density. Okay. Now we are looking for the relation connecting atomic polarizability alpha and dielectric constant epsilon r. Relation between alpha and epsilon r. Here you multiply this quantity to the left side, chi E into 3 epsilon 0 minus N alpha is equal to 3 N alpha. Multiply 3 chi E epsilon 0 minus chi E N alpha is equal to 3 N alpha. I keep 3 chi E epsilon 0 here. This time take it to right side and take N alpha outside. It is 3 plus chi E. That is, this chi E is equal to N alpha 3 plus chi E divided by 3 epsilon 0. Actually, we know the relation. That is, chi E is nothing but epsilon r minus 1, because we know the relation between the permittivity, relative permittivity epsilon r and electric susceptibility 1 plus chi E. From this relation, you can write chi E is equal to epsilon r minus 1. If I substitute this relation here and also here, that is chi E replaced by epsilon r minus 1 is equal to n alpha 3, instead of chi E substitute this one, epsilon r minus 1 divided by 3 epsilon 0. If I take this alpha, keep it here and bring all other terms here, this will be 3 epsilon 0 into epsilon r minus 1 divided by n. 3 minus 1, 2. Therefore, this will be epsilon r plus 2. This is the relation connecting the atomic polarizability alpha. This is a microscopic quantity. It connects to the relative permittivity epsilon r. This is a macroscopic quantity. This is called the Clausius-Mossotti Equation. If I rewrite it in another way, that is n alpha divided by 3 epsilon 0 is equal to epsilon r minus 1 divided by epsilon r plus 2. This is a Clausius-Mossotti equation. Okay, this Clausius-Mossotti equation connects alpha and epsilon r. This is the end of this unit. Thank you very much.